awful.
Yeah. So I will send you a link after that. So if recording is successful, I can. So okay. So we are a small number of group in the audience, but I think that we will have a pretty nice discussion during the talk, and there will be more people coming. So maybe I guess. But do you want to start now, or do you want to?
Sure, I can start now if you want. I'll go slowly anyway.
Yeah. Okay.
Okay. So I can start. You want to start recording or something?
Mm, yeah, I already started recording.
Ah, right.
So,
That's good.
okay.
All right. So,
Okay.
and
So yeah, let me introduce you first. But I don't have your CV, so I couldn't start from PhD. But yeah, Veronica Sanz is well-known phenomenologist and model builder in high energy physics theory, and we are good collaborator for some years. And she's based on University of Valencia on leave, originally from University of Sussex in the UK. So she will give a talk about the symmetry meets AI. So I'm looking for to interesting talk.
thank you, Hilmi. All right. So yeah, I'm going to explain the work that has been, written here in this article with Gabriela Barenboim and Johannes Hearn, who work in Valencia as well. And yeah, the work is about symmetry and its relation with artificial intelligence. And the title was inspired, the form of the title, by there is this short cartoon called Bambi Meets Godzilla, where essentially it's a very ridiculous cartoon where Bambi is just eating grass happily, and at some point Godzilla stamps on it. So it's a bit the parallel between the beautiful and innocent symmetry meeting artificial intelligence. All right, so let's see if I can, do this. So today we are going to talk about a few things. No? We are going to first start with what learning means from the human perspective and how this is paralleled and even improved by machines or tries to be better than human learning. Then we will talk about how artificial intelligence is such a powerful tool and is going to become more and more powerful than the tendency will be to simply surrender to its power, and whether we want to do this or not. Then we will talk about if we don't want to surrender, we need to understand what artificial intelligence is doing when taking decisions for us. And that is equivalent to try to look in under the hood of, let's say, the car, understanding the machinery inside. And then, as an example of this kind of mentality, I will talked about this paper that we have done, which tries to link physics and art through symmetries. My aim is that if you know about machine learning, that's good. You probably know about techniques, and you know the power, let's say, of machine learning. But hopefully, my talk will make you think a bit differently. And if you don't know about machine learning, I hope my talk that is kept at a very low level in terms of, let's say, terminology and so on, will motivate you to look a bit closer into this new set of techniques. Okay? And please do interrupt me at any point. Don't be polite, just interrupt. Otherwise, I talk and talk and talk, and I can do a monologue for hours. So that's not good. Okay? So let's start with this human versus machine learning. Let's talk about learning in general. So, what learning is? That's what we do all the time. We are occupied, especially in our area and our profession, we are occupied with learning. And learning essentially is taking some previous experience, something that you observed or studied and so on. And then with that, you do several things. For example, you can learn to repeat and improve on a task. So for example, you could learn how to make bread, and the first time it will be enough full bread, and then it will become better and better and better because you will learn from the previous experience and the mistakes you made, and you will improve on that. You can also use your previous experience to try to predict how situations evolve. So for example, you know that every time you wake up without taking a coffee, like it happens to me, then the rest of the day is not so good. So you learn from that and predict that you better have a coffee, otherwise the day will not be as good. I'm exaggerating, but let's say we are able to predict the evolution of situations based on previous experiences. Also, we have this capacity of hindsight. No, sometimes we recall the events of the day or the past few days, and then we start thinking about those and then discover unknown relations that we didn't realize at that point. Right? Sometimes we think back and say, that's why. Okay. We tend to be very, very good at make using this previous experience, but we know that happens when we do or not do things, and use that to choose the option that maximizes return. For example, I'm by nature quite a lazy person, so I tend to try to find always the easiest and fastest way to do what I want. And this ability to understand what are the things you can or cannot do in order to maximize the return is also very typical of humans. But one thing that goes beyond learning, let's say in animals, and really characterizes humans, and that's why I put this picture here, really like this picture of Bohr and Einstein, is that we humans can also take what we know or what we see, what we experience, and imagine new possibilities. This imagination we do have, of course, based on what we know, but bringing together elements of different situations and transforming them and making them into a new thing that hasn't been experienced before. Imagining new possibilities, this is thoroughly human. Okay, so that's humans. This is very impressive, and we could be tapping our backs. So, oh, well done, humans, we are great. It's fantastic, and of course, compare with other species, we do great, and we tend to dominate, let's say, thanks to this ability we have of learning. But we also know that human learning is limited. It's limited intrinsically, right? We as people, every person has their own personal viewpoint that is really based on the experiences they had or didn't have. Our collective intelligence is also very specific. For example, if you grew up in a particular culture or a particular environment, there will be things that you do feel and understand and can comprehend, and things that it will be very hard for you to comprehend. Even the language we speak, our mother tongue, might also limit the concepts that we are able to express in simple ways. Right? You think, for example, I wrote here "you speak" because if you have read 1984, no, that's this famous book. There is this passage in the book where this totalitarian regime is little by little removing words from the dictionary that they consider dangerous. For example, let's say freedom, thinking that if there is no word used for the concept of freedom, for people it would be more difficult to, make up this concept, talk about it, and then bring it forward. So our personal and collective viewpoints are limited, and there is nothing we can do about that. Of course, we in this audience, we know that what we do is try to learn more, acquire more culture, travel, understand others, be more tolerant, and so on, to broaden our base of understanding. But still, we will be limited. Okay, but apart from that, we are also limited because we are humans. We have a brain that has a capacity of processing information, and this capacity is inherent. For example, the amount of information we can keep in our brains, especially as you get older, I noticed the speed and the level of detail that we can keep is limited human by human. And that's why when we need to deal with complex tasks, we often form groups. We form cooperation and collaborations where different people bring different viewpoints. And that's what makes a more complex final product, right? For example, in our scientific collaborations, that's what we do. We bring people from different points of view and bring in different skills to make something better than an individual would do. It's very impressive. On the other hand, we know that machine learning is kicking hard, and its ultimate limitations, I would say, they're still unknown if they do exist. If we just think in the way machines are learning, meaning the physical basis of learning, we see that we went from many years of using CPUs to new kind of computing platforms like GPUs that have been used already for a few years, these graphical cards. But then there is this continuous dropping of new platforms like TPUs, FPGAs, IPUs, and so on, that I guess is not going to stop. Okay, so there is improvement in the way, speed, and capacity of machines to do computations. And beyond the, let's say, the von Neumann and the usual technologies, we know that there are new technologies coming up that may also lead to a substantial game change in terms of machine learning. For example, the establishment of quantum computing is stronger and stronger. There are other alternatives to the von Neumann kind of architecture. For example, with the use of neurophotonics, which could also lead to a strong change in the way machines learn. Okay.
Could I
Sure.
make a question?
Of course. Thank you.
I okay. I am I have some little bit of knowledge about machine learning, but well, because the data input for machine learning is determined by human, so I thought there is something limitation of to machine learning because the data for learn machine is determined by human. So
Yeah.
isn't it?
Mhm. That's very good. Yeah, indeed. Here, I'm not mentioning that to learn you need data, and the amount of data and the strength of that, or the robustness of this data might change indeed. But we do know. So you're right. For example, if I want to learn, let's say, about uh, images and learn to distinguish, let's say, I don't know, different kinds of buildings, I will need a vast amount of data and good algorithms to do that. But yeah, the initial point is always the data, and we need to have good data. I would say that nowadays, what we have is more and more data, and we need the problem often is the opposite. We do have the data, but we lack the manpower or the ability to deal with it. For example, in the LHC, the data is there, but we are limited by our ability to actually collect it. That's why we need to do triggers. Yeah, so a very good point indeed. there are limitations. And there is a limitation in the way machines learn, is that we need to give proper data. I would also say that there are now a lot of different algorithms that are being developed to take this data and actually without labels, labeling it automatically and so on. So this part is also being taken care of. There are improvements in how we deal with data as well. Thanks. Very good point indeed.
Oh, thank you for your answer.
Machines will only learn as well as the data we give, right? And then the rest is up to us to improve the algorithm. So this is very good. So coming back to the human learning, there are parallels of every one of these types of learning I discussed before in machine learning. Based on previous experiences or data related to that, machines can learn to repeat and improve on a task using, for example, in this case, supervised machine learning. The machines can also learn to predict the evolution of a situation, the time evolution of a situation, through sets of techniques that allow them to evaluate time series and learning through those. The machines can also be used to discover unknown relations with a sets of methods that are called unsupervised machine learning. Some of them are related to clustering and so on. There is also this whole set of relatively new techniques in machine learning that are called reinforcement learning, that is becoming incredibly powerful in giving only the instruction on improving on a particular return. Machines are learning how to do better and better on a task. And a particularly, powerful example of machines can do with reinforcement learning is that a few years ago, machines were able to beat the masters of Go, the Go game, that for up to that moment had been impossible for machines to do. Using reinforcement learning, we were able to make a machine beat a master of this game. And then this imagining new possibilities, which seems so intrinsically human and so difficult, is now being, parallel with some of these new techniques in machine learning, in particular generative artificial intelligence. For example, you might have heard about GANs, generative adversarial networks, or VAs, variational autoencoders. All those kind of techniques are able to generate synthetic new possibilities. Okay, so there is a lot of algorithmic advancements in machine learning that are really in parallel with the kind of things we are able to do and we are so proud of. Now, you probably, if you learn about machine learning, you know that it exists. Probably 10 or 15 years ago, you didn't know about it, maybe not even 5 years ago. And it seems like it's now everywhere. Everyone is talking about artificial intelligence, machine learning being a part of it, and talking about how we need to be careful about it, or it's going to revolutionize, the way we live is the next, a big thing that is happening. And it seems like machine learning is in the middle of a revolution. And you might think that this is due to our increased capability for data storage or data handling, or maybe because our computers are more powerful. But in fact, well, it's producing, I would say, this revolution in artificial intelligence is actually due to the way the machines are learning now. Okay, traditionally, when you had to teach a machine, a computer, to do something, what you had to do is to write some code, right? So for example, you wanted to teach a robot to move around, you would say, You will write lines of code like, if something is on the way, then you stop moving, otherwise you continue moving. So instead, an if and else kind of instruction. And based on these very simple ideas, the ifs, the fors, the do's, until then, and so on, we are able to write very complex codes, very complex things that can, for example, beat a chess master as well, right? So this is a diagram, if you want, of a very simple code, simple quote unquote code that is related to a game, a very simple old game, right? So by complexifying very simple instructions, we can end up doing very complex things. The problem with this kind of procedure, the procedure we have followed for until, let's say, now, we have been able to do progress with, is that this procedure is based on the thought of a human. The structure of thought is the one of a human. It's based on simple instructions like, if something happens, do this. Otherwise, continue doing something. Or, it is the kind of things that we can express with words, or that is based on really human concepts. The problem with doing this is that machines then can't describe relations that you haven't coded in. Okay? So as long as we keep coding things explicitly, the machine will not be able to do anything else than what we are able to think of. And in a way, we are limiting our machines in their ability to express complex relations that are not of that type. It's like if you were asking a born blind person to think on blue. I mean, it doesn't have the tools to do that. And in that way, we were limiting our machines to think. Now, this revolution that is happening on machine learning is mostly based on this new way of quote unquote thinking, which is the neural networks. The idea there is that instead of giving lines of instructions, what you are going to do is create an architecture, a structure, where this structure will be based on a very simple unit called a neuron, which will have some activation and so on. The neuron takes as an input some number and gets an output. By placing many of these neurons in a very simple structure, layers, and connecting them so that the inputs and outputs are interlaced, what you create is this network, neural networks, neural because it's made of neurons, and network because it's a network of those, which you can then use to say, well, okay, so given an input, pass this input through your neural network and get some outputs. And the only instruction I'm going to give you, neural network or machine, is that you keep repeating this again and again and again and again. And every time you go into the neural network, try to make it better. Do this better, like the description between the inputs and the outputs. Based on this passing through this neural network, make it closer to each other, closer to the data we know is true. So the network here is learning from data without structured instructions. There is no if and then, and you just say, this is my data that I want to describe. My data is based on some inputs and outputs. Go through this neural network as many times as you need to do, readjusting the structure of the network every time, so that at the end of the learning, you describe my data very well. And that's what all the instruction you are given. What happens is that although the neurons are simple, they're still non-linear. And because you have many of them interlaced in many, many layers, you end up being able to write down or express relations between inputs and outputs going through this network, they're extremely complex because you end up putting together lots of nonlinear transformations between inputs and outputs, all interlaced with each other, which leads to a highly nonlinear and complex way of expressing relations between inputs and outputs. So you could say that what happens to the neural networks is that the degree of expressivity, the kind of relations they can express in the data are immense, because they are also based on simple structures, minimal structures like these neurons, and they are parallelized, they're in layers. Their implementation into a computer can be made very, very fast. And this is this structure, this architecture based on these neurons, these neural networks, is what is really behind this big or speed up of the applications of machine learning nowadays. So, because they have this level of expressivity, they are able to tackle very complex tasks. In particular, they can tackle tasks that we thought they were really intrinsically human. And I want to spend just a few minutes with this because I think it's, let's say, it's important to think about this. So, for example, look at these pictures. Those are cats and those are dogs. And let's say people that have been, surrounded by cats and dogs, they probably can tell you that this is a cat. This is a cat. This. You see this girl here that holding something below a blanket. This is a cat. You are pretty sure it's a cat, not a dog. And then you see these things, and although dogs, they all look very different often, you can still tell that this is a dog, that this is a dog, this is a dog, and so on and so forth. This is obvious, no? You as a human say, there's a cat, those are cats, and those are dogs. I have no doubts. Now, imagine that you find someone that has never seen a cat or a dog or a machine, and you try to tell them few instructions of what you will expect a cat and a dog to be. Like you try to express in terms of characteristics what is describing what is a cat and a dog. Okay, so you will start by saying, cats, they have often long tails, although they sometimes don't. Cats tend to have pointy ears, although dogs, they also have pointy ears sometimes. Maybe there is something about the relation between the eyes and the nose, and it tends to be pinky, although sometimes it isn't. And also cats sometimes also have pointy ears, and depending on the dog, it can also be quite similar. I mean, think about it. It would be pretty complex to write down a set of sentences, a set of instructions, guidelines to distinguish a cat and a dog. You could do it. You could try to teach this without looking at many pictures. You could try to do this expressing the relations between or differences between cats and dogs. But could you do that? Could you teach a person or a machine based on these instructions, and that this person or this machine is able to identify a cat and a dog with 100% accuracy? And I guess you think about it, the answer is no, because there are many types of cats. Also, the pictures can be in, for example, these kind of situations. Dogs are incredibly diverse. We have been playing with them for too long. And if you had to write down what makes you know that a cat is a cat and a dog is a dog, it would be difficult to express it in terms of instructions. And that's the problem, expressing something. Identification of images like this is a complex task. The same for speech. It's also a complex task. And for very long, this complex task really was something unreachable for machines until recently. Until we started using neural networks. These neural networks, called convolutional neural networks, became very, very powerful and at without instructions, without a specific, look at the cat, it has a nose, and things, simply telling it through these kind of instructions. Given an image of a cat, learn is a cat. Dog, learn is a dog. And don't tell me how it's happening. I don't want to know. These are called the hidden layers. I don't know how this is happening, okay? Just do it. And then the machines are able to identify cats and dogs to the same level of higher accuracy than humans now. Okay, so that's a big revolution.
Is that
And
your daughter?
Mhm.
Is that your daughter in the picture?
No, no, it's a standard picture.
I see.
And my dog looks like a rat, so
Okay.
it will confuse a computer probably. Okay, so this technology, what I'm telling you, is really disruptive. And disruptive, is a buzzword. We like to say, oh, look, this is disruptive. You need to pay attention to it. And especially in this society we live where everything is, now and for now. And 5 seconds afterwards, we are changing. Disruptive may be a word that it has lost a bit of its meaning. But in the case of artificial intelligence, I think it really fits the description of a disruptive technology, because we are unable to predict how fast this technology is evolving. And we are unable to predict the extent of its applications. If you look at what's going on in artificial intelligence, new algorithms and new applications are coming up all the time, and surprising people working in this area as well. The only thing I wanted to tell you here is that you probably hear I say artificial intelligence and I talk about machine learning. Some people also talk about deep learning, and all these things are related. It's just that artificial intelligence is an old concept, obviously, that is very broad and has many things under its umbrella. Machine learning is a type of artificial intelligence that improves as they are exposed to more data. So they is able to reevaluate their learning with more data is included. And deep learning is a concept that refers to the use of neural networks, which can learn from huge amounts of data. So deep in this case is referring to these hidden layers in the neural networks that can be very, very deep. You have many of these layers. Okay, for example, typical neural networks that do image processing or image learning have 100 hidden layers. Okay, so moving on. So this is a disruptive technology is in parallel with our learning and surpassing it in many instances. So shall we just, give up in the sense of just embracing this technology? As you know, we've embraced all the previous technologies that were, breaking in and really bringing to humans something useful. And the idea is just, of course, we need to embrace new technologies. But first of all, we need to understand what they do. And these neural networks are so good at learning because they can scale very well with data. This is just a cartoon, but I think it's a good cartoon to express why neural networks of deep learning, these large neural networks, are breaking in, and they're going to be, let's say, what brings the most rewards in terms of artificial intelligence is because they do scale very well with data. Their performance, as you include more and more data, as all machine learning methodologies, they will improve. Right? With more data, they get better. But you also need to be able to handle data, as this colleague mentioned before. Data is important, and of course, if you have more data, you will improve your learning. But at some point, you will stop being able to incorporate it because your methodology, your method, is unable to actually incorporate all the subtleties that come with more and more data. Deep learning, deep neural networks are actually able to deal with lots of data and keep improving. Okay, so they are good at handling large amounts of data. This neural network structure that is based on layers and essentially 0-1 gates, these neurons, allows this high representation power, meaning that you can express very, very complex relations between inputs and outputs with moderate computational demands. And that's why they scale better. In particular, as you know, for machine learning, the use of GPUs is really like there are lots of algorithms optimized for GPUs. And it scales better than other learning methods, like support vector machines, to say something. They also have a good learning ability with little domain knowledge. What I mean by that is, for example, if we go back to our story of cats and dogs, you tell a machine, this is an image and I call it a cat. This is an image and I call it a dog. And you just keep showing images of cats and dogs, and you don't tell the machine anything about cats are of the feline type, and because of that they have this. You don't really need to know, the machine doesn't need to know anything about cats and dogs, what is their physiological properties or their behavior or so on, to distinguish them. They don't need domain knowledge. Whereas, somebody working veterinary will learn a lot about cats and dogs, and then they will understand that, for example, cats, because of their behavior, they need specific ways of, let's say, their morphology is adapted to their behavior. All this domain knowledge is unnecessary to a machine, to a neural network. Now, this it can be quite surprising because essentially you just need to give information, inputs and outputs to a machine, and it learns without needing more information, nothing around but data. And that's something that comes out sometimes as surprising to people who are not working in this area. Now, I want you to also think that that's something that also we physicists as humans are good at. As you know, many physicists, when they do physics, they end up not working in physics, doing other things. One of their good characteristics is because physicists, people doing physics, they mostly what they gain from doing an undergrad in physics is learning how to think. And because they do think well, they are able to use this way of thinking into other things. They tend to be successful in other types of endeavors. And deep neural networks are also good at this. They are able to take large streams of data and learn features with very little guidance. And in that sense, neural networks do look and work like black boxes. So
I have a question.
yes.
Yes. In this cartoon, there is vertical axis denoted by performance. Is performance means something like accuracy? Another time?
Could be one measure. Performance could be accuracy, or it could be, for example, if you are doing reinforcement learning, how well is your reward, how the reward you are collecting, how is improving. Performance, as defined in general, it could be many things, but yeah, accuracy is the simplest one.
Yeah, and I am just wonder about, because Raji and should have more processing steps. I think it should take more time to calculate something, but if it ignorable.
Yes, so if it's you mean if it's not supervised, you don't have a label? Yeah.
I mean, I asked about calculation time. the time of calculation. If it about if there is if I mean I think the more neural network makes more calculation time, but is it ignorable? I just ask that. Yeah.
Sorry. By the way, performance could also mean other things. For example, it could mean that you train a model, it gets 100% accuracy. You say, well, my model cannot do better. But performance, it could also mean that it's not true. 100% accuracy in that model based on that data, if you then use that model that you train and you obtain 100% accuracy, if you apply to another set of data, maybe the accuracy there, your ability to predict is really low or really high. So performance could also mean, in this case, the ability to generalize your model and to use it to other types of data. For example, it could be that for you performance, good performance means that you train a model that is really good at distinguishing cats and dogs, and is also really good at distinguishing models of cars, let's say, or stuff like this. Regarding time, computational time, nowadays we do more with less time, and is two types of improvements. One, of course, that we are able to use, if you go from a CPU to a GPU, your model is able to run on a GPU. You can go from days to hours, or from hours to seconds. But also, we are able to do more with less time because the models themselves, we can make them lighter. Once you train a model, you can make it lighter and run using what is called inference mode, and run in very simple platforms. For example, an edge device, something like a mini camera or a chip or an FPGA that you put inside a device. So you will say the more data we have and the more performance we are asking for when we get here, are we actually every time going to longer and longer time of computation? And the answer is no. It's not, because every time all these disruptive things that we are seeing is that every time we are finding, not me, but people are finding ways of decreasing the time that it takes to do the same tasks.
Oh, thank you.
Thank you.
Oh.
Thank you for your question. Okay, so here we were saying that, wow, so neural networks are doing lots of interesting stuff that I'm not able to explain because the way of thinking, quote unquote, is not something I coded in. And it looks like when it reaches a decision, when it gives a score, this score is really good if I train my model well, but I cannot explain how it reached that decision. So in that case, this is the typical problem of having black boxes, no? And you will say, well, what's wrong with black boxes? Fine, neural networks are doing very well, and you don't know why or how. Fine, I don't care, as long as they work. Plus a black box, the name comes from these things that go into the airplanes, and you only have to care about them if a disaster happens. Then you really want to open the black box and know what happened. So black boxes are related to disasters. And if everything works fine, why do you care? So if it works, why fix it? The neural networks are very powerful and can be quantified and tensioned against human performance of other techniques. So we do know that neural networks do work. They work very, very well. And for example, you know that your car works very well. And I would say for most of the people in the audience, we have no clue of how a car actually works. And we are not worried about it. We just know that by experience, cars have been developed with a set of standard procedures, and we do not worry about black boxes. And they are really useful. For example, here I'm just showing something I'm involved with, which is You can train a neural network to identify how earthquakes are happening, how seismicity is happening, and then you can use this neural network to do tomography, for example. And the way the neural network is actually learning how to do this, picking this seismograph, is not that relevant. What I know is that it matches the human ability and it does it much faster. And then we move on and use that ability of networks to actually do something else. So often it's a black box and it's fine because what we want to do is use it as quickly as possible. Okay, so why do I care if neural networks are black boxes? The problem is that if the neural networks and all these advancements that are coming through neural networks are through something we actually don't understand, first of all, I would say as physicists, this lack of understanding often hurts our private scientists, right? We, particularly theoretical physicists, we know that our job is to understand as much as we humanly can. And of course, there are limitations. For example, even to graduate students, I will always tell them that when we are doing quantum physics, they can wonder and be amazed as much as they want, but they will never reach the moment where they say, I do understand quantum mechanics. Like Feynman didn't, and nobody actually does understand. But still, we want to understand how things work, and simply using neural networks without understanding something, without opening this black box, is terribly, frustrating. Now, as it happens, whenever we try to understand something, what is going to happen is that trying to open this black box, we are probably going to learn a new way of thinking about neural networks. And these new ways of thinking, of expressing what a neural network is doing, is probably going to lead to new ideas for machine learning. So even if the effort is a forlorn hope, let's say, it's worth it, I will say, because it probably will bring new ideas. And there is a third reason, which I think from a social point of view is very, very important, which is the depth and the reach of AI in decision making is growing very fast. Let's say from whether you get a credit score or a loan or a particular diagnosis or a treatment, medical treatment, soon, if not already, is going to be supported by some AI-powered kind of algorithm. And our lack of control over this is worrisome. For example, a couple of weeks ago, the European Union showed or released a draft that they are preparing on trying to regulate AI and its uses, right? So there is all this worry about how neural networks work and whether we actually understand the ethical implications of the decisions made by AI. And in that area of trying to understand neural networks in order to evaluate its ethical component, there are things like explainable AI or ethical AI, and all these efforts do require a better understanding of the neural networks. So the upside is that neural networks do work very well and we can use them and we should be using it because it's a technology that is there and it will help us doing things that we were not able to do before. But the other side of things is that we also need to, in parallel, keep doing an effort to understand them better for ethical reasons and for simply learning reasons, for human learning reasons. So that's what I was calling looking under the hood or the bonnet in England, which is, okay, we don't know how our car works, but sometimes maybe we need to actually look under the hood of our car and try to understand how the engine is working. So this work that we released recently is precisely trying to do this from the standpoint of symmetries. So looking at the workings of neural networks through the point of view of symmetries. So symmetry is a key concept in physics. In this audience, I don't need to explain this. It's not just a simplification method, or it does not just allow us to relate different problems through symmetries. So at a deeper level, we know that the symmetries are behind every law of physics we know of, the understanding of forces, the stability of particles, and so on. Symmetries already can help machine learning with machine learning problems. For example, in problems where we know a certain level of rotation or deformation is allowed, then we use it to augment the amount of data we use for learning. And this is called data augmentation. So at least symmetries are already taken into account in some methodologies in machine learning. And we also know that this concept of symmetry is part of our shared human appreciation. So we know that symmetries play a role in how we appreciate things. For example, here is a miniature, and the picture looks beautiful, I would say, and faces of people in general are pleasing to us because they have elements of symmetricity or symmetry in them. And also they are beautiful when they are not exactly symmetric. For example, if Emmy here had been looking at us straight ahead, instead of just tilting the head a tiny bit and looking at a tiny bit non-symmetric, then the picture wouldn't have been so pleasing. So as humans, we seem to appreciate certain levels of symmetry, and maybe not exact symmetry, but just approximately broken symmetries. So what we did.
Myung has
Yeah.
a question, right?
Hi, him.
Hello.
Hello.
Veronica. Yes, I have a question. So you talk about the CNN data augmentation using the symmetry, but I understood is that the reason that this works because the CNN doesn't know the symmetry, right?
But CNN has symmetries embedded in them. These convolutional and translation symmetries are precisely implemented in the CNNs. So that's the convolution, when the neural networks do this convolution inside, that is precisely a transformation that preserves symmetries of translation and relative distance symmetry. So that is it. Convolutional neural networks do have symmetries included in them. That's why they are so
translation. Yeah, translation and this, but they don't have the rotation symmetry, right?
No, they don't, indeed. And here, in data augmentation, this means, the typical benchmark. The idea is that these symmetries are just symmetries in the sense that you can maybe rotate this a tiny bit, a bit of the angles. In the 8, for example, you could flip them, so it could have a Z2 symmetry. And you can also stretch these images a tiny bit. You cannot really do a full symmetry rotation, but it's some amount of symmetry. Yes, there is, and we use it. So when we say data augmentation, what we mean is that we take an image and we do certain transformations, and we assume this new image is also a good image and also represents the class we are trying to learn. And this is through some level of symmetry. Is clear, Mehul?
Okay, thank you very much.
Good, thanks for the question. So, fine. So symmetries might be a way to understand some of the behavior of these neural networks. If we see whether symmetries do play a role in the workings of a neural network. So we ask ourselves whether machines can deep learn symmetries, how, and how we could use this for. So there was this paper by Krippendorf and Sivari, which was called Detecting Symmetries with Neural Networks. So we thought, wow, wait, this is the first starting point. We should look at this paper. The problem is that this paper was looking for a very specific type of output, which was trying to detect symmetries in to classify vacuum and string theory, blah, blah, blah. And what they did is, at the end of the day, is an algorithmic way of finding symmetries. Okay, so it wasn't deep learned in that sense. So in the paper, it seems at some point that they say that if you take the hidden layers and this input in the last hidden layer, and you do clustering, you will find a situation like this where the symmetric potentials are able to cluster, and there is the applications of these clusters. And they didn't use this, but they mentioned this as a, let's say, something that was significant. But what we also learned is that actually you take a non-symmetric potential and you do clustering, you will get exactly the same as well. So the level of symmetric or not symmetric is not actually behind that. The non-symmetric potential will also show clustering and replication, because that's what clusterings do, okay? So this didn't cut the chase, actually. We had to then ask ourselves whether there are other ways to learn about symmetries, which do not rely necessarily on this level of duplication, and also a way of detecting symmetries that has nothing to do or is able to deal with situations like this one. So here is an Escher drawing where it's called night and day. And you can see that as a human, we know that there are some level of symmetricity, right? So you see the birds, there is a set to symmetry, you know, if you change the colors and just flip it, there should be some level of symmetricity, right? And there is also, we have this chessboard, so we know that elements in this image are replicated and so on. So this work that I mentioned before will not be able to deal with this kind of situation. So we had to find another strategy. And what we needed a very general procedure. So that's what we set up in this paper. We started with something else. Instead of starting with some, potentials in string theory and, doing these kind of things, what we started is with potentials, but at the not a depiction of what you will say is something symmetric. Like if you had a kid and told him or her, do drawings of circles, it will do something like this, no? It will do circles, 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 okay? And you will say that this corresponds to an O2 symmetry, rotation symmetry in 2D. And it had to be a procedure that didn't depend on color, because we see that there is symmetry here, and we see that there is something that we think is symmetry in here, whether it's in color, in black and white, and the same is here. But there is something beautiful about this drawing or painting, of Van Gogh, independently of the painting being in color or black and white. And we also needed to set up a task that was universal enough that will work for physics potentials and will work for inputs of any kind. So our task was simply take an image, separate it in bins of X and Y, and on whether there is black or white inside this bin. And we train a fully connected neural network to reproduce the image. So our first task to identify the presence of symmetries was do that. Have an image, this, or this, I don't mind, bin it, and with a fully connected neural network, be able to train this network to actually reproduce this image. And this is the first task. So the idea is that we did this task, a fully connected neural network. This fully connected neural network had no clue of whether there was symmetry or anything. The task it had was simply learn to reproduce this image. And then we could ask whether doing that task, the neural network had to learn about symmetries, did learn about symmetries. Okay, so in practice, we train a fully connected neural network made of physics templates, like this one, images like this. And we trained fully connected neural networks for all of them so that they were able to reproduce the images. We paid attention for this neural network to not over-specialize and not overfit. So it actually had to learn to reproduce the image, taking shortcuts, being smart. And then what we did is to take the PCA, let's say the dimensional reduction of the hidden layers of all these fully connected neural networks and looking at them. So the part one of this algorithm, that it has to be very general, so that's why it has two parts and is of that type, is that we fed lots of images, potentials, right? And without telling them about any kind of symmetricity or anything. And then we took the last hidden layer, we look at the input of that hidden layer, and we did a PCA representation of this data. But here, at that level, there is no symmetry, there is nothing. It's just saying, learn to reproduce that image. Now, if this neural network, while trying to reproduce the image, had realized, quote unquote, the presence of the symmetry, the PCA might encode this learning. So what we did then is the following. We took a second part of our algorithm is the following. Is we took all these PCAs, which, again, they look different depending on the random seed that they start for. There's no feature in these PCAs that we humans can identify as anything. It's not that symmetric or not symmetric were different, nothing. No, it's really a PCA with a density of points somewhere. Even though at first eye, at simple, human eye, there was nothing there, we still, took the PCA, knowing that, for example, the PCA came from rotation symmetric situation, set to symmetry, continuous translation, discrete translation, or no symmetry. And we collected hundreds of them. And we generated a second task. And the second task was PCAs with labels. And we ran this to a CNN, and we saw whether the CNN was able to classify, given a PCA, what symmetry this PCA came from, what kind of symmetric situation or non-symmetric it came from. So what we found is that the PCA was, using PCAs and these labels, we were able to classify the symmetries to a good accuracy. Let's say it was a multi-class of where we were getting 70–80%, right? Which then told us that the PCA, although by eye couldn't see any difference, did encode some level of some information about the symmetry. So going back, when we ask the first neural network to reproduce the image, part of this information about the symmetry was encoded in this last hidden layer. Okay? And the proof of that is that the PCAs of this last hidden layer with labels allow us to actually do a good symmetry classification. So without telling the network to find symmetries, it did find them, and we could decode that information by taking this PCA and running a classification. So yes, when you ask a network to describe an image, it seems to be able to realize whether this image has some level of symmetry in it. And it's even able, at least given the PCAs that we obtain, to say what kind of symmetry to some level. It's not perfect, but it does. So then once we have this procedure, then we can use it, because now we know that for any image you give me, I can process it in black and white, leaving only the main lines, what you will say, draw this image. And then I can ask through this procedure what level of symmetry is finding, what kind of symmetry and to what extent. And this can be used for any image. So we thought a nice way of representing these applications was precisely to use it for art. And that's the last part of my talk. So fear not, I'll be done in 5 minutes. So far, what we have developed is an algorithm which takes simple images and produces a symmetry score. And it can be used to any kind of 2D images, a children's sketch, a painting, a photograph, anything, right? So what we did is take examples from art. Then, for example, this is a drawing by Kandinsky. And then we train this full connected neural network to learn this plot. Essentially, what you're telling the network, the fully connected neural network is, please look at the picture, look it very well, very, very well, very, very well, very, very well, so that you are actually able to reproduce this picture. Okay, so it does, it transforms this image, first image into something more abstract. As you go into hidden, more and more hidden layers and deeper, ends up really simplifying this information. This is a PCA into essentially what is the background and what is the main drawing lines. And again, as I told you, you as a human don't see anything here. And any drawing you give is going to give something like this, of that kind, of some separation. So the question is, can I do this for drawings, paintings, where I know there is symmetry or there is no symmetry, or I know, meaning that I perceive as a human a level of symmetry and see what my symmetry score is. So taking this PCA, can I pass it through my second CNN, my classifier, and see what is the symmetry score? And that's what we did for many things. But here I'm just giving you a few examples that exemplify what happens. For example, when we put the Kandinsky, from all our categories, which is no symmetry, rotation symmetry, continuous translation, discrete translation, and set to reflection symmetry, with this Kandinsky, what it sees is that there are elements that are repeated, all these squares and all these circles, and what it does is says, from all the symmetries or no symmetry, what I assign to this Kandinsky is a very high level of translation, discrete translation symmetry, which is totally what you will say as a human. For this night and day that I showed you before, it will say, okay, so it gets some level, mostly a level of discrete translation, because there are lots of elements that are repeated, all these birds, the squares of the chessboard and so on. It gets that there is a level of Z2 symmetry, right? Because it's true, this image, when you, through this access, you flip it, you get a very similar image. It gets that there is some level of translation symmetry like this continuous, and it also gets that the image is not completely symmetric because there are things, elements that are not similar. Same for these other Escher horses, the horsemen. It gets repeated elements, this TN. It gets that there is a flip symmetry, and that's it. It's really from the PCA of the fully connected neural network trying to understand this picture. This fully connected neural network is realizing that there is a TN and Z2 symmetry, and is using it to learn how to describe this picture. It is able to say, well, there is this horse here, but this is exactly the same horse here, so they need to do it 2 times. I don't need to do it for each of them. I actually realized there are repeated elements. Same for this plot over here. This is a drawing by Picasso of a woman with a beret. And it realizes that it's mostly non-symmetric, because it has elements that are not equal. But it also realizes that, as all human faces, there is some kind of Z2 symmetry. Same for this Van Gogh, where he sees that there are repeated elements, all these lines. and there is a level of reflection symmetry. And another benchmark is Pollock. Pollock is this guy that was doing drip paintings, which are, you know, I don't know, they are actually obviously non-symmetric, and he finds that they are obviously non-symmetric. Okay. And we did many more, including children's drawings, fractals, photographs, etc. So to conclude, I would say that we are just starting to understand the applications of machine learning in physics. There are many applications that are coming up, and more that are going to happen next years. And if we want to go as physicists or theoretical physicists beyond a mere iteration of our traditional, of a mere iteration what is done in the literature, we need to understand a bit better how algorithms work. We know that this machine learning is a very efficient black box, but a black box is never enough, I would say, to us. And we would like to try to, let's say, even though we cannot understand as humans everything that the machine is doing, at least we should try to communicate with the algorithm with tools that we do understand. For example, here we do understand, we perceive there is a symmetry. And that's also what the machine has done. So today, hopefully we learn that AI does identify and use symmetries when it's asked to do a task, which we call a decoy task. And this learning can be found in subtle features in hidden layers. We applied this method to art, finding that the results, the scores given by this AI does match the human intuition. Our next steps is to many of course that one can do is we could go from images to sound, another artistic expression, so from paintings to music. Our algorithm is good for two-dimensional representations, but so we are going into higher dimensions by modifying the decoy task. And of course, we would like to use unsupervised or generational AI in order to go a bit deeper and farther in this direction. And that's all. Thank you very much.
Thank you very much. Very interesting talk. So yeah, I think that I guess there are some questions. Please.
Hey, Veronica, I have another question.
Go ahead.
Okay, 형도 first.
Thanks. I understood that your PCA doesn't have information about the specific symmetries, but in the last slide, yeah, you showed several symmetry groups that you used, O2 or TN, or so. If you already know this specific symmetry, then it just looks like the usual Fourier transformation or the mode decomposition of using spherical harmonics or Bessel functions. So compared to that case, I mean, if you know the answer that there is a Tn, then you can use this Fourier transform to figure out, I mean, what is the exact lattice spacing or whatever. But compared to that, what's the merit that you did here?
So here I didn't know what the symmetry is. What I mean is that I don't know what the symmetry is here. What I'm telling you is that as a human, I say that there must be, I feel that there must be some level of Tn. But it's like there are repeated elements. So it's not, I haven't assigned symmetry to this. This is the score that is given by the algorithm. All what I'm saying is that it corresponds to your human intuition.
Yes, so I think you provided the meaning to the label. Let's say I can call this index as 1, 2, 3, 4, 5, and then how did you?
Yeah, let me go back again through the algorithm. Has two parts. One is this decoy task, where the task is to learn to reproduce the image. There is no information on symmetry. Now, and then from that we get this PCA. Now this decoy task, we repeated it many, many times, right?
So this is the O2 example that you are.
So we repeated this decoy task many, many times for many examples where we knew exactly what was the symmetry in there. And that allowed us to collect lots of PCAs from the first decoy task and place a label on them.
Yeah, so I'm asking, how did you fix the label? I mean, why did you call this the second one as O2 rather than just a random label? Yeah.
No, it's not, no, precisely, yes. So we generated lots of images based on physics templates, physics potentials that had an O2 symmetry, many of them.
Yeah.
We passed them through this decoy task where we didn't give any information about that thing we knew. We knew, but the machine didn't. And then we collected all the PCAs generated by the machine and we place a label on them, O2. This is Z2, this is T, Tn, and none, the empty box. So the idea is that by doing it this way, we can then place anything that has an image that has no exact symmetry or is not of the type that a physics potential will be, and will still work. Right? Because we just place again this any of these kind of images, we pass it through the decoy task, we get a PCA, and with that PCA, we ask a score to this, let's see, to this thing.
Right.
We take the PCA, we ask for the score, and this is this output here.
Yeah.
And yeah, that's the point precisely. If we now know that the images have, I mean, you have to start with something you do understand in order to benchmark your algorithm. So what we know, we start with templates that are known to develop a procedure that can be then used to templates that are not exact, but still you can say, yes, my machine is doing right. It's going in the right direction. And the idea precisely is to then look at databases whose symmetry properties you do not know or even infer or you don't have an idea about, and then use exactly what you were saying. Let's say if I identify in a database that there is a high level of TN, I look for it and I try to understand why what are the elements that are repeated in this database. If I find a high level of Z2, precisely I try to infer or find what is so deep in this database leading to Z2. Or you can do data augmentation using that precisely. If there is a Z2, you can take all your data and then flip around that axis. There is no symmetry.
I think I was expecting something like a fractal structure or some amorphous structure which cannot be inferred from those mode expansion using Fourier transform or
in the
state
paper.
Harmonics. But your example is just something that we know, so that's why I was asking. Okay, but I fully understand the point.
Excuse me, you do not know. No, you do not know, Sally. You do not know that this painting has a Z2 symmetry. Certainly, you cannot give a number to it.
So those I mean this weight is summed up to 1, and then it just represents the importance of this symmetry factor. But
exactly.
is there any
you do not know
for that, or
you do not know that, and you cannot compute it by looking at the painting. And in the
no, I'm asking. So is there any meaning to that? So suppose that some figure has G2 factor 0.5 and the other has 0.25. Is there a difference in them? Can you quantify that, or is it just a kind of a qualitative thing that maybe there is some feature of G2 hidden in this figure.
So you tell me, I mean, if you
I'm just asking, I mean, how important is this number?
Even though I understand, but first of all, you do not know this. You look at the picture, I'm saying that as a human, you will feel that there is maybe some level of Z2, but you don't know what it is. You don't know that level. And what it means is that in this image, there is about 60% of the image that could be represented using Z2 symmetries. And what it means then is that you could simplify the representation, but that's what the machine is doing, representation of that image using Z2 to that level, to the 60%, they say here. Or in this case, what this is telling you, this score that is so high, is telling you that actually this image, to a large extent, can be expressed by thinking on the repetition of the same elements. So you are quantifying that. And what I'm saying is that we did that for images that where we could talk about them. And the point is that now we can use this to any data set where we don't have an intuitive representation and still give a score. But it means that, again, the score 60% means that 60% of this data represented by this image can be, is duplicated because there is a Z2 symmetry. And in the paper, I didn't show here, but we also showed fractals and also found, you know, the typical global features of having a Z2 repetition of elements, Tn and so on. So we do analyze fractals too.
All right.
But
Thank you, Young-Won.
We only shows, I see, fractals.
Any other questions?
So
Yeah, Veronica. First of all, nice to see you.
Nice to see you too.
And I feel very sorry that you cannot drink coffee together after seminar. By the way, so your work, your paper is so beautiful that I cannot resist to print it out, even though I don't have enough ink. Okay.
Sorry, yeah.
So no, so literally so beautiful. Yes. I have a very simple and stupid question. So for the example, I think that your algorithm detecting some kind of the global pattern, the global symmetry. Yes. The first example, you have the circles. You have many circles there. And I'm curious whether you can also find the local structure, local symmetry, like a O2, because you have the circle.
That's a very good
question. Do you have
question.
any idea? Yes.
This is to be done, and we haven't done it, but you see that the fully connected neural network was just asked to, the decoy task was to represent the whole picture. So it's finding global structures that will allow this task to go faster, no? That's why it only sees these global structures, this Tn that is global. But for example, if we had asked the decoy task to also do segmentation, so to actually try to understand parts of the picture as well and get very good at this as well, my assumption, and we haven't done it, okay, so it's not that, is that it will also identify local structures. It's just that we gave a very simple decoy task of look at the whole picture and identify and do it very well, about 90-something%. But if we had said also, you need to identify, do segmentation and go through different parts of the picture and also identify them very well individually, it will have found also local symmetries. But I don't know, because we haven't done it.
So for example, this simple example, I think that your algorithm will go empty, right? No symmetry.
Yes, this one?
My image that on the camera. Yes, we have the Japanese flag here on the right here. In the whole picture, you have this.
You mean this Pollock over here?
No. So, can you see my video? There's a Japanese flag here in the big campus, the circle here, right?
Let me see. I need to find your image.
Oh, okay.
Yes. We
Yes,
try
yes,
that.
yes.
We try that to with drawings from our children. And
yes.
you know, it's funny. Many times he was given a very low score in symmetry, no? So he was given mostly 0 when the children do whatever.
Yes.
But they often start doing, for example, the typical house with the chimney, the tree, the sun. He was finding a level of symmetricity. Mostly Z2s. He was finding some TNs. So, yeah. But yeah, I mean, this is 0 level things. We are like a first step. And then hopefully it's not us who had to do all this, but the local features, you say correctly. Can we go beyond can we apply it to anything that is not images, but music, for example? And that's something, yes, we are pursuing a bit. And also we did like these 2 tasks that were supervised, but we should also use unsupervised. Generative AI is there to be used. So lots of things to do and no time, you know. Hopefully someone else will do it before. Okay, more questions, guys? If not, I think you're ready to.
Yeah, we have some discussion. Do you have any more comments? Questions?
Yeah, just one thing about your quotation of Feynman on quantum mechanics. I think actually we don't understand quantum mechanics if you really focus on this measurement or wave function collapse process. So it's more than just quantum mechanics. Is we're just that our level of understanding on quantum mechanics is exactly what Feynman says. So,
I do agree. It's
okay.
and it's thing. I don't know, the way I interpret it is that it's simply by the way we think as humans, we don't understand it. Of course, we can write, and that's the beauty of mathematics. We can write the equations, we can draw conclusions, but understand as we do understand processes, phenomena, and so on, we do not. And maybe it's just impossible for a human to do. And that's also the power of mathematics, no? It's beautiful. That's why I like to tell my students, because when you start with quantum physics, you say, wow, it's awesome. But you also expect that at some point you will understand why this is happening. And they need to, I think we need to surrender to the fact that we won't be able to understand. And it's a bit the same for this machine learning. The way it learns is not our way of learning. So I think it's normal that we do not understand it, but we still should try to find ways to express it. That's why symmetry is maybe one way, but there must be many others that we should develop. I think it's important, especially for these ethical considerations. So we do not understand. I agree.
Okay. Thanks for the nice seminar.
Thank you for your nice questions, interesting questions.
Can you apply your result to distinguishing cats from dogs and with other, hierarchy experiment?
So
do you mean symmetry of cat?
The features. You are talking about features of the input.
Very good question, Hyun-Min. And to do this, we will need a bit what Myung-Hun was saying. We will need to go from global to local, because the symmetry structure that we extract so far is global features. So, for example, is the decoy task is looking at the overall picture. It's not looking so much into the individual. It's not doing segmentation and looking at the nose and in so much detail. So the answer is maybe, but we will need to improve on the decoy task we are given so far. And it's work to do, and since it's very computing intensive, is not the kind of thing that I will embark on doing first. I'm not, I'm a theorist and I'm
Maybe
not very good
it's
at
better
computing.
to ask question. Maybe if you look at the CMB, you look for some features from heavy particles in addition to standard vanilla inflaton perturbations. You could look for something else, and there might be features embedded in the cosmic microwave background. So then
Exactly.
the features might be depending on, the UV physics, but can you, it depends on the physics template, but if you cannot capture it by spherical harmonics, I don't know if you impose certain symmetry, I don't know, some discrete symmetries,
I know
triangular symmetries, I don't know.
it's a very good question. It's like, imagine that instead of one of these things, you feed to this neural network the CMB or different modelizations of the CMB. Then, and the task will be learn how this CMB is distributed, but without any other, it's like in this case, it was learn to reproduce the X and Y, every pixel of the CMB. And in that learning, maybe indeed there is something here that has learned that we hadn't noticed. And by looking at this hidden layer and so on, we might be able to find a non features of the CMB. Exactly, this idea in general, which is when a network, a machine is learning something, it might doing shortcuts, so it might be realizing of features you as a human hadn't realized. This is the idea in general, and this is one particular realization. But yeah, one could think on even feeding different CMBs and seeing whether there are these global features that is learning about. Again, this is just the first zero level step and a nice application to art because it does a beautiful paper, but it's a proof of concept, but it is so many things one could do.
So I need to put your plot in the frame to put it on the wall.
With a score. No, that's I'm not very artistic oriented myself, but I agree, it's beautiful. I like more Escher and that's it, very geometric stuff.
Okay.
But yeah,
I want to learn this. I want to simulate with the different pictures.
And the CMB is a bit like us, no? Like this, no?
Yeah.
It's a mess, but still, if we feed many CMBs, it will be able to get rid of the background of what is not important from what is important. So maybe it's worth thinking about a particular task that one could give the machine. Okay. Open questions.
Okay, thank you. I enjoyed your talk. I think that everybody else also enjoyed, probably.
Thank you.
Yeah, thank you for your talk. And I think that hopefully we can meet again in a workshop.
Yeah, that would be nice.
And have a nice discussion again.
Thank you.
Okay. Okay.
Thank you for your great talk.
Thank you.
Thank you.
The Myung-Won suggested a short talk with you after that, Veronica.
Okay.
Yeah. So maybe would you mind remaining in the Zoom for a moment?
Sure.
After everyone else went out, we can talk.
Adiós, Adriana.
Kiss.
Encantada.
Okay, thank you to everyone for your participation. Okay, see you next time. So there will be another seminar next week. So, okay. So Myung-Won, do you have some idea?
Yeah, two person still here. One person, I'm counting down.
Okay. Okay, everyone.
Okay. No, I just want to chat. Yeah, so actually, I really love your paper. Really.
Thank you.
Yeah, so this is the most beautiful paper that I have seen. Though I don't read any paper, by the way.
But this is
Okay,
thanks to
so-
the artists. It's the artists will make the paper nice, not me.
So yeah, this your paper is about some kind of the apparent symmetry that in the data, right? In the picture. But how about that if there's some hidden symmetry that like some experiment, like Hamiltonian, we have some symmetry, but in experiment there's some pattern that we don't know. Maybe you can have this apply this kind of thing a little bit further to get some